Hello everyone, welcome to my YouTube channel. My name is Jish and today I will be discussing our project on data correction codes of discrete mathematics. In this video, we will explore the significance of a single bit, the story behind Hamming code's creation, how it works, its advantages and disadvantages. We will also discuss an alternative method that overcomes limitations of Hamming code. Let's dive in. The importance of one bit. Have you ever wondered how a single bit, the smallest unit of information, can hold tremendous power in the transformative world of big data? Let's take example. In 7th October 2008, flight number QF72 was flying from Singapore to Perth. At the height of 37,000 feet, the autopilot 1 disconnect automatically, so pilot connect autopilot 2, but it shows lots of error, so pilot decide to fly manually, but after some time flight get out of control. Somehow it control the airplane and done emergency landing. In that many people injured. After inspection, it was found that the aircraft's flight computers receiving incorrect information about the aircraft's angle of attack, AOA, which refers to the angle between the oncoming airflow and the aircraft's wings, which happened due to bits changes. Reason for that bit change: 1. Air pollution, 2. Cosmic rays, 3. Noise and interference. But the main reason for that is cosmic rays, because it's so powerful, at the height which flight was flying. It was for sure that cosmic ray effect was more than at the ground. So, you can probably say that this is the main reason behind wrong information transferred. There are several other places at which you can understand the importance of one bit. Like in Mario game. And in voting machine error, in 2003 at Belgium. I will be providing link if you want to see the beauty of one bit. The invention of Hamming code. The invention of the Hamming code is credited to Richard Hamming, an American mathematician and computer scientist. He made significant contributions to the field of information theory and error correction coding. In the late 40s and early 50s, Hamming was working as a researcher at the Bell Telephone Laboratories in New Jersey, where he was involved in developing early computer systems. At that time, computer memory and communication systems were prone to errors, and finding a reliable method to detect and correct these errors was a critical challenge. Hamming recognized the importance of error detection and correction in computer systems and set out to find an efficient solution. He proposed a method that would allow the detection and correction of single-bit errors in data transmission or storage using a systematic approach that could be easily implemented in computer hardware. Hamming's breakthrough came in 1950 when he introduced Hamming code. Hamming published his findings in a paper titled Error Detecting and Error Correcting Codes in the Bell System Technical Journal in 1950. His work received widespread recognition and became a fundamental concept in the field of error correction coding. The Hamming code provided a practical solution to the problem of error detection and correction, enabling more reliable computer systems and communication networks. How to use Hamming code with a table. Let's take one binary. In this type of code we have to calculate parity first, so we are arranging the information bits in a 4x4 matrix in such a way that they do not occupy the positions for parity bits. Now we have to decide that if we want odd parity or even parity. Odd parity means number of 1 is odd. Even parity means number of 1 is even. We take this for example. Step 1. You have to take second and fourth columns at a time and count 1, and if there is odd 1 then parity bit is 1 other than 0. In this example we have odd number of 1 so parity bit is 1. Step 2. You have to take third and fourth columns at a time and count 1, and if there is odd 1 then parity bit is 1 other than 0. In this example we have even number of 1 so parity bit is 0. Step 3. You have to take second and fourth row at a time and count 1, and if there is odd 1 then parity bit is 1 other than 0. In this example we have even number of 1 so parity bit is 0. Step 4. You have to take third and fourth row at a time and count 1, and if there is odd 1 then parity bit is 1 other than 0. In this example we have odd number of 1 so parity bit is 1. Step 5. You have to consider all bit to count 1, and if there is odd 1 then parity bit is 1 other than 0. In this example we have odd number of 1 so parity bit is 1. Now we sent this encoded message. Suppose 1 bit change in that and now message is. For decoding part again arrange in 4 times 4 table. If you want to know the error position so for that mark location that has 1 in box and XOR all of them you will get 10. If you check and XOR is 0, then it is not always 0 error, but if you check then you will find that it's total even parity but subpart doesn't have even parity, it has odd parity. 2-bit error doesn't solve by Hamming codes. Advantages of Hamming codes. Hamming codes detect and correct single-bit errors by adding redundant bits to the original data. This helps maintain data integrity and reliability. The code is simple, systematic, and has low overhead. Hamming codes are designed to detect and correct single-bit errors. The receiver can compare the received code word with the original data to identify any flipped bits. The Hamming code can correct single-bit errors by determining the location of the error and flipping the corresponding bit. The Hamming code follows a straightforward and systematic approach to error detection and correction. It involves adding parity bits at specific positions within the data. The Hamming code introduces minimal redundancy to the original data, making it advantageous in terms of bandwidth utilization and storage requirements. Hamming code can be adapted to different data sizes and error correction requirements. In summary, Hamming codes are efficient, fast, and reliable for error detection and correction. Disadvantage of Hamming codes. 1. Limited error detection and correction. Hamming codes can only correct single-bit errors, but not burst errors, which limits their effectiveness in certain error-prone scenarios. 2. Increased redundancy. The inclusion of redundant bits in Hamming codes improves error detection and correction but also adds transmission or storage overhead, requiring more data to be transmitted or stored compared to the original information. 3. Limited error correction capability. Hamming codes can detect the multiple errors, but cannot accurately correct them within the same code word, necessitating alternative error correction methods or retransmission. 4. Complexity of implementation. As the size of the data and code increases, implementing Hamming codes becomes more complex due to the involved mathematical operations and computations. 5. Increased latency. The error correction process in Hamming codes introduces a delay in transmission, which can be undesirable in real-time systems that require low-latency communication. Types of error correction codes. There are several types of error correction codes, including Reed-Solomon codes, BCH codes, turbo codes, LDPC codes, and convolutional codes. Widely used for error detection and correction, Reed-Solomon codes can handle both single-bit errors and multiple errors. They are capable of correcting errors in larger blocks of data. It is more powerful in multiple errors. BCH codes, it can correct both single-bit errors and burst errors. A burst error refers to a cluster of consecutive errors occurring in a data transmission or storage system. They are an extension of the Reed-Solomon codes and provide a higher level of error correction capability. 1. Satellite communications. 2. Magnetic storage systems. 3. Digital broadcasting. Turbo codes are a class of iterative error correction codes that provide excellent error correction performance. They are capable of correcting multiple bit errors and can approach the theoretical limits of error correction. Turbo codes are extensively used in modern communication systems, including mobile networks and satellite communications. LDPC codes are offering high error correction performance with low decoding complexity. They are widely used in wireless communication systems and digital video broadcasting. LDPC codes are known for their capacity approaching performance, and it was used in many modern communication standards. Convolutional codes are a type of error correction code that operates on a continuous stream of data. They can handle various types of errors, including burst errors, and provide efficient error correction. They are commonly used in applications that have real-time requirements such as mobile communications and satellite links. Different types of error correction codes have different strengths and weaknesses. Understanding the characteristics of each type of code is essential for a particular application. Understanding the power of one bit and the evolution of error detection and correction techniques is crucial in ensuring reliable communication. Thanks for watching.